This is the 36th lecture of this course. We were talking in the last lecture, we were talking about that now our aim for some time our aim is to bring the nilpotent matrix of a nilpotent operator into the simplest form. Again, by simples here, of course, I would try to make as many zeros as possible to be there, and among the among the non-zero entries possibly which are in the off diagonal areas, then I will try to make them as 1, because the entries in the diagonal, they do not create that much trouble. The complicated entries in the off diagonal positions, they make the situation more complicated, it seems so. So, therefore, we will try to do that. Hence, we will start with, as usual, a finite dimensional vector space. So let us make a definition here. So, finite V is finite dimensional, and let lambda be an eigenvalue. Eigenvalue for t, eigenvalue for t. So, given this eigenvalue t are finitely many non-zero vectors, finite sequence of non-zero vectors. I mean, whenever I say sequence, that means it is ordered in the way they are appearing, that is by the index, is said to be a Jordon string. A Jordon string corresponding to Jordon string with lambda, some people call it with eigenvalue lambda or corresponding to lambda, maybe that is better, because they may not be eigenvectors, you will see soon, corresponding to the eigenvalue lambda if the following happens, that lambda V1, lambda V2 plus V1. So, in general A Vi plus 1 is lambda Vi plus Vi minus 1 for all. No, I cannot, for all I from 2 up to k. Okay. So, this is so try to understand that the first vector is an eigenvector, the second vector V2 is being mapped to lambda times V2 plus V1, and the same pattern goes on. Okay. Or you can see from here that if you consider the operator A minus lambda here. So, the first vector V1 goes to 0, the second vector goes to V1, and similarly the last vector goes to Vk goes to Vk minus 1. Okay. So, that is what So, we call this as a, if this happens, then we call this as a Jordon string corresponding to the eigenvalue lambda. So, the first observation is, if this is a Jordon string, then this has to be linearly independent. Linearly independent. Why? That is easy to see. Suppose this is 0. Remember how the operator A minus lambda I acts on these. So, if R is the largest positive integer, such that CR is 0, then we do have, so other coefficients are already 0, CR VR is 0. Okay. Now, you apply you keep on applying a minus lambda I on this on the both sides. When you apply it for the first time, then the first term goes away. Applied second time, the second term goes away. So, in the when you apply it for the rth time, what you will have is times Vr Cr, this is 0. Now, the way these are defined, you can immediately see what this is. So, if you have, so here it is very clear that a minus lambda I times to the power I times Vi is 0, right? Yeah, because a minus lambda I, once you apply it twice, then yeah, then it will be 0. So, because at every step it is pushing it one step backwards, okay, fine. So, therefore, this becomes Cr times V1, which is 0, all the vectors are assumed to be non-zero, that forces Cr to be 0, which is a contradiction. Sorry, first the Cr is non-zero. See, this is a contradiction. So, once we have a Jordon string, this, I mean any string, any Jordon string corresponding to a vector corresponding to a some eigenvalue lambda, we have seen that this is going to be linearly independent. Okay. So, therefore, now if we consider, let us say define W to be this, then and then certainly W is T invariant. Why not? Because each Vi, the image of each Vi is the linear combination of the I mean image of each Vi lies in the span of V1 V2 Vk, right? Right. So, T is W is T invariant, and then what next? What is the, so if we call this, so there this set, let us denote it for the timing S, and so this S becomes an ordered basis of W. So, therefore, T restricted to W. If you look at the matrix of T restricted to W with respect to this ordered basis, how will the matrix look like? T V1 will be 0 and certainly others will be 0, then T V2 it will be V1, so there should be lambda, then again and these all will be 0. Now, when it comes to T V3 is lambda times V3 plus V2. So, here I will have 1 0 lambda and then all 0. So, therefore, you see we will have such a scenario. Okay. The matrix will look like this. So, if therefore, this is a very, I mean this is indeed a very simple form. It has only some diagonal entries and most of the off diagonal entries are gone, and whichever are there and the other non-zero off diagonal entries are 1. So, perhaps this is the simplest form that we can expect. Okay. If T is to begin with diagonalizable, then even those 1s will not be there. So, for general situation, this is the simplest form that we can expect. So, therefore, we would try to bring the matrix of a general linear operator into block diagonal forms where each block will look like this. So, let me make a definition here. So, these are called so matrices of this form, these are called elementary Jordon blocks. The reason for calling it elementary will be apparent later. Elementary Jordon blocks, maybe I can just simply say Jordon blocks. It will be a Jordon block corresponding to lambda. Okay. So, by a Jordon block corresponding to the eigenvalue lambda means I will mean a matrix of this form. So, well, we denote this by j lambda, and sometimes, and you see that a Jordon block corresponding to lambda will be is uniquely determined by its size. Okay. So, given lambda, if I specify the size, let us say k, then there is exactly one matrix of this form, right. So, sometimes of size k, if we write so, all of size r, we usually write it jr. So, jr lambda is an r by r matrix such that this happens. In particular, when r is 1, we will have only the scalar matrix lambda. When r is 2, it will be lambda lambda 1 and here 1, here is 0. Okay. Fine. So, we would try to, so as I have said that given a general linear operator, I mean given a linear operator, assuming its minimal polynomial splits, now I will try to find a basis for in such a way that the block diagonal matrix that I am looking for will be of this form, that will be that along those blocks will be precisely Jordon blocks corresponding to the some Jordon blocks corresponding to the eigenvalues. Okay. So, now my aim is clear. Okay. Now, let us go ahead. So, first as I see, as we have already convinced that we should rather start with nilpotent matrices, nilpotent operators, because once we have something for nilpotent operators, then for a general operator it is not going to be a problem, right, I mean for those blocks, because only diagonal along the diagonals the eigenvalues, the corresponding eigenvalue will be added. So, let me explain by sticking let me explain by considering the case of by considering special case of nilpotent. Am I doing so? Well, let us see. So, what I am saying that try to understand. So, let us stick to a very special case. Suppose T is nilpotent, then lambda has to be 0. Okay. So, once lambda has to be 0, then for any Jordon string, the corresponding subspace, the matrix will look like this. So, everything 0 is a strictly upper triangular matrices. So, along just above the zeros in the principal diagonal, I have 1, in every column I have exactly 1 and then again everything is 0. So, if A is nilpotent, this is going to be my case, and for general A. So, what I mean is, suppose I mean I can for a nilpotent operator, let us say, let us be simple, for a nilpotent operator, I mean for an operator T, we consider by passing through on the by passing to the by passing to the, let us say, on just generalized eigenspace. Suppose I can suppose I find a Jordon string such that this happens, such that the Jordon string, then on W the matrix of T, suppose for this nilpotent operator I can find a Jordon string, then we define W like this, then on W this is going to be the matrix of T minus lambda I, and naturally on W the matrix of T is going to be nothing but, right. So, this is what I was talking about then. So, the upshot is to bring the nilpotent matrix in a way that bring the matrix of the nilpotent matrix in a way that you have only such Jordon blocks for that matrix. Okay. Yeah. So, enough I have talked about for nilpotent enough, yeah, as I have talked enough that we should to convince you that we should rather work for nilpotent operators. So, now we should do that. So, there Yeah, so let us come to the, let us hit the main theorem, that is better. We have defined Jordan block all this, so let us try to let's go. So let be nilpotent. Then there exists Jordan strings well, here have to be careful regarding notation. So since for nilpotent operator lambda the eigenvalue is only 0, so I will drop this part from the notation, and to label them I will rather use this this superscript. So J1, J, let us say Jk Jordan strings such that, so it will have some size, I am not mentioning what the size is, such that yeah, such that this is a an ordered basis. You can simply say ordered, because order is order comes from the way they appear, ordered basis of V. So this is what we will prove now. Yeah, this is what we will prove now. And what is the, and what we will achieve after proving this? This is following that if we denote Wi by as the linear span of the ith Jordan string, then since this is the basis, yeah, since this is the basis, well, I further need to mention that, well, so there is, so because the way I have written, it might seem that this Ji and Jj, they might be, or there might be overlap, then I should further insist that for I not equal to j. So just to make sure that they are different. So if I call this as Wi, then since this shows that this is the basis which for which this forms a partition. So therefore, once I have, if I have this basis, then V becomes the direct sum of Wi's, okay, and then therefore the matrix of T with respect to this basis, you will see is in a very usual form. So so it will be certainly, it will be a block diagonal form. In the first block, you will have a Jordan block of this form 0 0 0, and the length of this block is same as the length of this Jordan basis, then this, and this goes on. Okay. So once I can prove this, then that shows for any nilpotent operator, I will try to understand, once I can prove this, then that shows that for any nilpotent operator I can found a basis. So such bases are called Jordan bases. Okay, the basis such that which is the disjoint union of some Jordan strings, such bases are called Jordan bases. So for nilpotent operators, if I can find a Jordan basis, then immediately with respect to the Jordan basis ordered naturally, the matrix becomes the diagonal block diagonal matrix, where along the diagonal we have Jordan blocks of the corresponding size. Okay, and once we prove this, then for a general matrix, then I mean having proved this theorem, it is now an immediate consequence that, so we have not proved this theorem, let us assume this theorem for the time being and try to understand its consequence. So, this is the general theorem. So, let V be a finite dimensional vector space and T be a linear operator. Assume T empty splits over F, then T has then there is a then so see one thing, a Jordon basis that involves the the Jordon base, the definition of Jordon basis depends on the linear operator we have with us. So therefore we should rather call it a Jordon basis for T or of T. Okay. So then there is then T has a Jordon basis. Try to understand, usually we call the vector space as a basis, okay, but here we are slightly deviating. We see that T is having a Jordon basis. What it means is there is a basis of V which is also a Jordon basis for T. Then T has a so what I mean by that is what we mean by that is, or in other words, so first let me explain what I mean by a Jordon basis for a general operator T. So here the only assumption that we have taken is empty splits over F. So it has a basis of this form. So what this means is it has a, so we have a basis of V of this form, let us say so I am not well, so the basis might be of this form. Suppose for lambda 1 I might have have to be somewhat more careful for 1 for I can have multiple things for lambda 1. So for lambda 1, okay, right, let us try to, the notations might be somewhat J so okay, so I should rather this is the notation is somewhat complicated here. I should choose an easy notation which does not make it more complicated. So we will what I am going to say is we will have Jordon. So a Jordon basis means is the disjoint union of certain disjoint union of some Jordon strings. So for nilpotent operator, all the Jordon strings have to be, I mean all the Jordon strings are they are having eigenvalue 0, but here we can have multiple Jordon strings corresponding to an eigenvalue. So you have to formulate that in that proper way. So let us say for so for so better that I should mention their size. So how does one write this, that so we will, what I want to write is I will have several Jordon strings, but corresponding to each value, one value I can have multiple Jordon strings. So for lambda 1, suppose so if I assume that I have okay, so let's use this note on the subscript, let's use this notation 1 2, let's say for lambda 1 I have m1 Jordon M1 Jordon strings. Okay, for lambda 1 I have M1, I have M1 Jordon strings. I am not specifying their size when I need, because that will make this notation more complicated. When I need that, then I will specify. Let us say for 1 union and I am not I am assuming throughout that this is a disjoint union, that no two have any intersection in common. So, that I should simply write disjoint union. So, then M2 lambda 2, therefore, okay. So, that is a basis of this form. Okay, I think I have again messed up some notation, because this j I have started using for okay, fine, let's stick to that. Well, I should not, there is a, disjoint union here, there also I need to change, because I have messed up with the notation. Fine, messed up with the notation. There exist Jordon strings such that, here I should make here it is simple, because the point is I started using the same notation for the Jordon string and the corresponding Jordon matrix as well. So, let us not do that, because for it might be possible that for two different Jordon strings the Jordon matrix might be same, that is possible. So, we should reserve this notation for the matrix. So, we would rather simply write this j1 up to j k. So, j1 up to j k. So, these are Jordon strings. So, thus these are non-zero subsets of V j k such that here the matrix must be of this form. So, the first you will have some size a Jordon block corresponding to 0 having size n1, okay, where ni is the size of zi, So, therefore, I should do it here. So, it has a Jordon basis, that is a basis composed, well, I should rather write the simple one, Jordon basis, that is the union of disjoint union of Jordon strings Try to understand, even for a general operator, by a Jordon basis I mean a basis which is the disjoint union of some Jordon strings. Okay. So, Jordon basis means union of strings such that, or now in other words, we have a basis, we can bring the matrix of T in the into the following form. What is the form? So, first, so we will club the Jordon strings corresponding to same eigenvalue together. So, let us say the first we will let So, first let us club the Jordon wave strings corresponding to the eigenvalue lambda together. So, suppose corresponding to eigenvalue I have Jordon strings having length r1 up to corresponding to lambda 1. Suppose I have Jordon strings of length r1 up to rk. So, therefore, j so this is the length yeah, this is actually somewhat, the notation seems to be slightly complicated, please bear with me, because otherwise I do not, right now I can think of a better way. So, first rk number of blocks okay yeah for lambda 1 let us say I have n1 number of blocks. So, corresponding to lambda 1 okay, because I have corresponding to lambda 1 I have let us say n1 number of Jordon strings in that Jordon basis with length from r1 up to n minus 1. Then for each of these strings, when I consider its linear span, I will get an invariance of space for which the matrix, once you restrict the linear operator on that, then the matrix will be of this form, this elementary Jordon block. So, these are the Jordon is a block diagonal matrix where first few blocks, first I will write down the blocks corresponding to the eigenvalue lambda 1, then the blocks for lambda 2 will come up, blocks for lambda 2 will come up, yeah. So, r1 up to okay. So, do I so rn1 r1 n1 okay. Then maybe for lambda 2 I have blocks of this size okay, r1 2 up to n2. So, therefore, so that is how you see the matrix will look like. Okay. Fine. So, therefore, this is what we are looking for, and why is this true? That is very simple, that on V lambda I, if minimal polynomial splits. So, let me first give you the justification that why this well, if I call it the theorem 1 and this is the theorem 2, why theorem 1 implies theorem 2, that is very simple. So, based on this assumption I have this, and now I restrict. So, the matrix of, so what I do is T minus lambda I times I is nilpotent on V minus lambda I, right, is nilpotent V lambda I. So, we use theorem 1 to get a Jordon basis for the operator T minus lambda I. So, the matrix of T minus lambda I on V I will be so matrix will be with respect to the Jordon basis of this, for this operator you will have Jordon blocks of possibly different size along the diagonal, and each block will have vector corresponding to 0. So, let us say you will have, and for this you will have your matrix will look like this, right, and once we have this, we have already seen from that when we that is the matrix for T minus lambda I, and from that what with respect to the same Jordon basis, the matrix that the matrix of T will be nothing but T on this space will be nothing but the same things, with just the same size Jordon blocks with same size will arise, but the eigenvalue will be lambda I instead. So, keeping notations, borrowing notations from here, n k lambda I. Okay. I think I have written A throughout. Yeah. So, if this is the so if this is a Jordan string corresponding to like an eigenvalue lambda of A, then this the same set becomes a Jordan string corresponding to eigenvalue 0, corresponding to eigenvalue 0 for the operator A minus lambda I, right, and vice versa. If I have a Jordan string of A minus lambda I corresponding to eigenvalue 0, if I have so, then that string itself becomes a Jordan string of eigenvalue lambda for the operator A. That is easily seen, right? Yeah, lambda V1. Then A minus lambda V2 is, just make sure that so A V2 minus lambda V2 will be lambda 1. So, what A V2 will be lambda V2 plus lambda 1. So, the Jordan basis of a Jordan string of vectors, Jordan string of A with respect corresponding to eigenvalue lambda becomes a Jordan string of the operator A minus lambda I corresponding to eigenvalue 0 and vice versa. Anyway, so therefore, once I have a Jordan basis for t minus lambda, this operator restricted to on here, from that we get a this gives me a Jordan basis of t restricted to Vi corresponding to eigenvector corresponding to the eigenvalue lambda. Okay. So, thus therefore, we get that the matrix of t on lambda I, we can bring it in this form, and then finally piecing when we put, I mean, for each lambda I have a matrix like this, and finally we need to put them along the diagonal. That gives me the that proves this theorem, right. I repeat, I mean, pardon me for using confusing notations in the beginning. Now, the notation is simple. So, already we have seen that this becomes a nilpotent on this generalized eigenspace. Then we use theorem 1 that enables us to write down the matrix of this operator like like this. Okay. And once we have written the matrix like this, we know how to get the matrix. We know how to get the matrix of t on V lambda I, that exactly becomes the diagonals are changed to be, the diagonals should be changed by lambda, and everything else will be same. And when in each Jordan block corresponding to 0, if I replace the diagonals by lambda, then it becomes a Jordan block corresponding to the eigenvalue lambda itself. So, this is what we get. Okay. So, in view of theorem 1, theorem 2 is now clear. Therefore, given a linear operator, I know, so this part is also clear why you have a Jordan basis, because on each V lambda I you have a basis, which is a disjoint union of Jordan strings. So, on each Vi you have a disjoint union of Jordan strings which constitutes a basis of V lambda I, and then for each lambda I you will have such things. Now, you take the union of all of them. So, it will be so many Jordan strings corresponding to different eigenvalues, but all of them they are to be distinct certainly. Okay. Fine. Okay. So, we have proved theorem 2 modulo theorem 1. Now, for the rest of this lecture, we will try to prove theorem 1. We prove theorem 1 by induction. Yeah. One, by induction. Induction on what? On n, what is n? Dimension of V. Okay. So, to be technically true, what should I prove? That for any n, whenever I have a vector space of dimension n over F and a nilpotent operator, then it must admit a Jordan basis. Okay. Fine. So, we prove by induction on n. So, therefore, we will have to show it is true for n equal to 1. How to prove it for prove this true for this is true for n equal to 1. So, n equal to 1, if n equal to 1 and if t is a nilpotent operator, then t must be 0, right, because nilpotent operator one dimensional vector space. So, the degree has to be less or equal to 1. So, degree is exactly 1 and okay. So, for n equal to 1 is trivial. Okay. So, assume for n equal to m, assume for n equal to m. Now, we prove for n equal to m plus 1. By the way, so before we prove that, let us exclude a trivial case from the first place itself. For example, what is the trivial case? If T is a null map, then any basis, then if you take any basis, so the I mean each basis, each singleton subset of that basis will be a Jordan string for that vector, for Jordan string of length 1. So, for null map any basis becomes a Jordan basis and the corresponding Jordan blocks are having size 1. So, to begin with we assume T is non-null, T is non-null, assume T is non-null. T is non-null. Okay. So, I think in this lecture it will be I may not be able to finish the proof. So, let us go ahead and then we will pick up. So, let me give you the idea for the proof, then maybe the detailed proof I will be doing in the next lecture. So, since T is non-null, then we look at image T. So, image T, this is of course a subspace of V, right. Can it be trivial? No, because image T is trivial means the whole it will be a null map. So, image T cannot be trivial, image T cannot be trivial. Okay. Can it be equal to V? Remember from V to B, image T is whole of V means T has to be, by diagonality theorem T will be invertible, but since T is nilpotent, T cannot be invertible, no, because nilpotent means it will have an eigenvector corresponding to 0 and that so therefore, that vector T V is non-zero, T V is 0. So, therefore, it cannot be invertible. So, therefore, image cannot be full. So, image, if we call it of V prime, V prime is a proper subspace of V, that is V prime dimension of V is strictly less than n, and of course, V prime. So, as T commutes with T, so the image of T commutes with that is invariant under T, right. So, therefore, we can talk about the restriction of T on V prime, we can talk about the restriction of T on V prime, and so therefore, since T is nilpotent, its restrictions also have to be nilpotent. So, it is a nilpotent operator on a vector space having smaller dimension than n. So, by induction hypothesis, by induction hypothesis, one has a Jordan basis of V prime with respect to t v prime. So, our idea is the following, that from that Jordon basis of v prime corresponding to the restriction operator, what we will do for this restriction operator, we will extend this Jordon basis to a Jordon basis of v. So, starting from that Jordon basis of v, we will construct a for Jordon basis of v prime for this restriction, we will construct a Jordon basis, we will construct a Jordon basis of v for the original operator t. Okay. And let me just give you the idea how to get this Jordon basis, then with that I will finish. In fact, I may leave everything to you, by giving the idea I can leave the rest to you for as an exercise. So, let the Jordon basis for this operator, Jordon basis of v prime for this operator is, let this be following: v11, v12 up to v1n1, this is a Jordon string, v21, v2n2, vk1, vk2, vknk. Okay. Let this be the Jordon basis of v prime for this operator. Now, this, so what I mean by this, so these are the Jordon strings whose disjoint union is the Jordon basis. So, since these are the Jordon basis and t is nilpotent, so the eigenvalue must be 0 corresponding to this basis. So, they are corresponding to this string. So, this force says, let us say t v11 has to be 0, right, because it is a Jordon string corresponding to 0. Similarly, t v21, t vk1 is 0. So, what we have is v11, v21, vk1, they all lie inside kernel T, right, they all lie inside kernel T, and they are linearly independent because there is a part of the basis. So, we extend this to Z1 up to ZR, extend. So, extend this to a basis of basis of kernel T, right, extend to a basis kernel T, and then remember that all of them lie. So, all these last vectors, they lie in image. So, that means they must be, so there must be a vector, let us say for each I, v I n I must be the image of some, right, because they are, this is the vector in image. So, therefore, we add one more vector v1 n1 plus 1, v2 n2 plus 1, similarly vk. So, when we enlarge, when we add one more vectors in this fashion to every string, you see that this also becomes a Jordon string, right, because this it has the required property. So, thus we have a huge set, namely the union of all these together with these extra vectors. So, find this together with Z1 up to ZR. So, you have a huge union. The claim is this is a Jordon basis for T. This is a Jordon basis for T. I leave the proof as an exercise by giving you a hint. So, the hint is the following. Just take a minute. Just take a minute. So, the hint is the following, that use rank nullity theorem to show that these are, so what is the number here? So, number is like R. So, well, I have to finish early. So, I have to finish soon. So, first using rank nullity theorem prove that these are correct in number, that is the number they are n in number, right, and then finally you, so since they are n in number, it is enough to prove that this set is linearly independent, and that is then you directly prove, taking a combination and applying T, you directly prove that as linearly independent. So, they are n in number and linearly independent, so there will be a basis. Okay. So, this is what the proof is, the verification of linear independence I am leaving to you. So, okay, with that I will finish this lecture. Thank you.